今日はあっち側行ってきましょうかね。日光街道の先に行ってきましょうか。
And so there's a concept of big data also, so that's an evolving. What I'm talking about today will be different next year, but at the top there is a fork way, then we get talk about things I'm playing. That's my design. And of course it's a 5 terabyte drive. It's 6 times of my laptop, and that's from last year. You can get even bigger ones now, or smaller ones, for the sake of more data. I'd say 15 years ago, I purchased a 1 terabyte hard drive for a data center at the cost of $250,000. 14 years ago. So it's things have evolved. Things have evolved, and they will continue to evolve. So this is a related slide that Mark had earlier today. It's the whole idea of cloud computing and the size of data sets and where it needs to move data from one data center to another data center. One of the reasons why it's becoming practical to do so is that it's going to take years now to move large data sets. And 5 petabytes is about the scale. It's a bit smaller than that, but it's the order of magnitude that the ICGC data set is in right now. So this is a 1 to 1 in 5 petabytes. And so that kind of data size set is not going to be movable into a data center anymore. And if you want to have access to the whole data set, if you want to be comprehensive, if you need the whole data set for the kind of questions you want to ask, then it's going to be impossible for one host and 2 to get, because you're planning to use it. The folks at Amazon, if you actually talk to them about moving large data sets like that, you tell them it's pretty much instructions, just a shit ton of points. And it's shipping stuff. Or to actually, and what has become the solution now is to actually move your software to where the data is and do the compute there. And that's what we're going to do this week. And we're going to do it in a couple of environments. The first one, we're going to do that in Amazon's public commercial cloud provider, Amazon Web Services. And in the second half of the week, we're going to do it at the Collaboratory, Cancer Genome Collaboratory, which is a resource at the University of Toronto that's been set up by folks at the OICR. And so it's going to be, you'll see very different access, somewhat different access, somewhat different. What's going to be the difference, though, is which data set is where, and which data set is present on Amazon versus on the Collaboratory, and which tools are easily integratable and pipelines and so forth. And so you'll be playing with that this week, and you'll have a chance to study that, to see the differences. So what I just said, data sets are in the petabyte scale, if not exabyte, pretty soon. And data and the security rules, same thing, I'll talk about, will be somewhere not in your own hands. So basically, it's a lot easier to apply standard sort of rules for accessing the data around where the data is, as opposed to supporting those rules around your laptop. And you should not have to get this data on your laptop anyway, because it's stealable and not physically secure and so forth. And so not necessarily the data we're going to study this week. So this week is going to be, we're going to talk about controlled access data, but the actual data you're going to be using is going to be open data, because we didn't get you permissions to have access to controlled access data. But you'll see how to do that in lecture today. So we talk about openness, there's all sorts of different things. So there's open access, usually refers to publications. There's open source, which usually refers to source code. Open data, which refers to data. And then open courseware, which refers to the material that we teach with here at this workshop. And so we talked about, just so the bioinformatics relation is databases. And the way this information is organized is sort of a key thing to understand what is usable for a given database. And it sounds a little crazy, but if you put something in a database, you should be able to get it back out. I've had experiences with large-scale projects where we put things in databases and then we can't find it anymore. And it all has to do with identifiers and the fields of the metadata and where things are at. That's not kept track properly, and the wrong identifier is put in the wrong field, and then you use your query engine, which looks for that metadata in a certain field, but doesn't look in the other field, and it doesn't find it. And this has happened in large organizations, which will remain nameless because it's too embarrassing. So it's some of the big players that are on this planet in the bioinformatics field. Maybe you should give me a beer, I'll tell you. No, you don't buy me a beer, but if I have a beer. So obviously, once a database is well organized and well structured, and it sort of standardizes ways you can talk to it, then you can write tools that will do that. So it's not just you doing head queries to a web interface. You can write APIs. So APIs, the application programming interface, allows you to talk from software to talk to your database and generate your own interface, your own website, your own data sets, and so forth. So having that available is a really sort of key thing to having a good database. And the really sort of key thing on organizing your database is what's your data model. And so here's an example of data model would be that whenever I change the DNA sequence in my DNA sequence database, I will modify the unique identifier for that sequence. Because the unique identifier for that sequence is X, Y, Z, is 0 for those 3 letters. And I change one nucleotide, and now to know that the system has changed, my data model says I will change the identifier for that because it's not the same sequence anymore, and therefore it has a new identifier. And so databases like EMBL and GenBank have done that now. It wasn't like that at the beginning, but now they have identifiers that change whenever the sequence changes. And so that's what the data model is. So whenever you change a sequence, are you going to change the date stamp on it? Yes, we're going to do that. If you change a feature but don't change the sequence, you change the date stamp or the unique identifier for the sequence. All these rules that you put around a database is important to sort of define up front before, and you publish those ideally, or you at least put them on your website to explain to the people what these various fields mean, what is the purpose of this database, what's being maintained, how frequently is it getting updated, and all of these things. And so those are key things in thinking about a database. And so just a few images to sort of explain some of the things we think about. So the metadata, which is basically data about data, right, is you can have things like names, dated, submitted, ORCID, does it mean what ORCID is? Researcher, yes, it's each of us, we all have an ORCID ID. If you don't know the ORCID ID, you should know the ORCID ID. If you don't know, you can go to the ORCID website and they can tell you what the ORCID ID is, or you can register and have the ORCID ID. And so all journals are required that anyway. So when you submit a paper, many of the journals, definitely the PLOS family does that, and the BMC, many of the open access journals, and ideally this will percolate to things like PubMed and so forth. So you'll be able to query by ORCID ID for an investigator. So it'll be a lot better because there's some names you can imagine happen very frequently in databases, but represent different people. They just happen to have the same last name in the first initial, and so this will protect for that against that. So the publisher, book title, and so forth. So the data would be a DNA sequence file. That would be an example data. A cosmic record. Does anybody know what cosmic is? So it's a somatic database. I'm going to talk about it a bit later. Protein interaction data. So you know what that is. We don't talk about it in this course, but so interaction database. Intact is the biggest one probably at the EBI, and that's a database where you say protein A interacts with protein B. It's usually protein, but they do protein DNA, protein RNA, protein small molecules, and so it's this entity interacts with that entity, and so the record is A binds to B. You may have more metadata saying which part of A binds with which part of B. A binds to B only when B is phosphorylated, and so forth. There's all sorts of metadata you can put around that. But the protein interaction database is an example of a record. Titles of book or books themselves. So a storage system could be a box on your shelf. That's a storage system. Oracle, MySQL is sort of commercial and open access relational database systems. Binary files could be a place where you're just a file system. Text files and bookshelves. So a query system could be a list you look at. So you have a list of all the things that are on your bookshelf, and you say, I'm looking for this book, where is it in my list? And so you can just look down the list, and that's sort of a query system. A catalog is a query system. An index file is a query system. SQL, structured query language, is a query system. Elasticsearch, which are now used in cloud computing, or systems that allow to look at big data, is another query system. And grep, which is a Unix tool, which you all practiced last week, right? Grep, yes. Okay, good. So test you on that later. No? You forgot? You already forgot grep? Grep is a good one. Anyways, we'll come back to grep later. And then the information system. So the information system is like the whole echelon of CV. Google is like an information system, right? But the Library of Congress is a library system. It's an information system. I'll tell you NCBI is an information ensemble at DBI. UCSC Genome Browser is actually multiple browsers, multiple organisms. It's a whole sort of information system with the parts talking to each other. And ICGC is also a big information system that we'll talk a bit about today. So all the information system is sort of the big envelope, the ship that you label that has a reference often that you can refer to. But under it, there are many layers of things that are key to understand as well. So NCBI itself allows your system to submit data, to download data, to learn. It has a whole teaching section. It has a whole development and tool section. It has lots of analysis tools and research and just places where you talk. The NCBI itself is a core group of really good research, and so there's research is available too. So we talked about the DNA sequences and how they're shared and so forth. And actually, the nucleotide sequence are part of this international nucleotide sequence share system where three centers, so the Europeans, the Americans, and the Japanese, share the data, the content of their respective databases. There's 3 points of entry into one database. So you sequence is submitted either through Europe or Japan or the US, Bethesda, NIH, and NCBI, ends up into a GenBank DNA, European Nucleotide Archive, or DBJ, DNA database of Japan, into one repository. And they each issue accession numbers for records that were submitted to them. But let's say a GenBank accession number will be in the DNA database and will be queryable with the same accession number. So it doesn't get a European accession number because it got one already from the US. And so these three databases sort of sync up every night. And so they're actually, within a day, they're the same database of each other. And so it's a really sort of good example of sharing the load of submission, updates, and maintenance of the archive and the whole repository across 3 different countries. It's sort of, and the other sort of benefit that is there, which was not done at the time, was actually you have basically a help desk in 3 different time zones. And so you have, whenever you're awake, you can sort of call somebody to help you. And hopefully, if you're only looking for the night and you're in North America, you can call the Japanese people. But they all have email, and so, there are basically this help around the world for this resource. NCBI, of course, has many other things besides sequence data, and so this, if you go to this query page, you can actually put in the query all filters and square bracket. It gives you the number of records in each resource, and so it gives you an idea of how big. If you look at previous lecture notes, I have this slide every year, so I update it every year, so you can go see how much the database is going. Go do that exercise. guys see how the resources have grown over the years. And so NCBI offers PubMed and PMC, dbGaP, and CleanVar for health data, WGS and RefSeq, an example of the genomic data, their sequences and 3D structures in the proteins world, and in the chemical world they have PubChem and biosystems. So it's just a very sort of quick overview of the types of things that they do. Now I'm going to switch a little bit and talk about file formats. And so, I'm specifically talk about DNA sequences. And I'm not going to even go, I know, for example, Jared tomorrow is going to go into details of the BAM file format, and I'm not going to do that today. But it's, and VCF, I think also, others later in the week may do VCF files. So you'll have that throughout the week, all the various file formats that you have to work with. Right now, there's actually, on the UCSC website, there's, where the UCSC, there's actually a really good sort of table which has definitions of all the various file formats, or many of them that are used in the DNA world and RNA and DNA nucleotide world. And I invite you to go look at that if you're interested in that. The databases are now, I've sort of split them, I've sort of done that for a few years now, so I've split them into two sort of classes, two categories. One is like a primarily archival, and the other one is secondary or curated, although some sort of fit in both sides. And so GenBank is not really curated, although there is some curation that goes on, and curation being sort of what Trevor was talking about, the sort of the handwork that has to be done on records, that it doesn't, it's hard to automate and so forth. And so archival tool, like a resource like GenBank, Unicode is a protein resource, PubMed, which is all the abstracts, PubMed Central, which is all the open access journal abstracts, Intact is a protein interaction database, ICGC, the data for that, EGA is sort of the, it's not sort of, it's the equivalent of dbGaP on the European side. And so then secondary databases where some curation takes place, RefSeq. So RefSeq was actually, when NCI was invented, RefSeq was a way to take, so the issue with the GenBank records is that they're archival and they belong to the user or the submitter that submitted that record. And then NCI wanted to have a system where they wanted to update those records and they couldn't update them because they belonged to the submitter. But what they did is they didn't, but they're part of an open access database. So what they did is they took the best, and also, for example, beta-gal, which is a very common gene in bacteria, for which there's probably been sequenced 10,000 times. So there's 10,000 entries of beta-gal in GenBank. But what we at the time wanted to do with RefSeq is to have one copy of everything. So one copy of the E. coli genome and all the genes there, and one copy of the genome and all the genes there, and every organism else and so forth. And so RefSeq is a reference sequence of each organism in the database. So how does NCI get that data? Well, basically it goes from the existing compendium, and they take the best one they think is the best one, and they take it to the best memories, and they curate it so that they curate it in a standard way across all organisms. Most of the time it's